For this example, we'll work out two different trigonometric integrals that involve powers of sine and cosine functions. So the first of these, we have cosine to the 7th x times sine cubed of x dx. And for this one, we're in good shape because both of these are odd, which means we have one extra of sine or cosine to pull off to the side to make our du term, which will allow us to work this out just by substitution and not require any of the half angle formulas that we would need for other things when powers are even. So because the sine term has a lower power that's still odd, I'm going to convert everything into cosines and integrate that way. So to do that, I'm going to rewrite the first integral as integral of cosine to the 7th of x times sine squared of x times sine of x dx, saving this to be my du eventually. I'll convert the sine squared into cosine squared using Pythagorean identities. So this will become an integral of cosine to the 7th of x times 1 minus cosine squared of x, and then a sine of x dx. So I can now make my substitution. U is cosine of x, and du is sine of x dx with the minus sign. I can then plug that in, and if I do, I will get this is integral of u to the 7th, 1 minus u squared times du, which is now just a polynomial in u, so I can work out the integral. Give me a u to the 8th over 8 minus u to the 10th over 10, and I'm missing a minus on the entire thing from this minus du over here. There's a minus sign here, here, here. I can then plug cosine back in for u to get a cosine to the 10th over 10 minus cosine to the 8th over 8 plus c. Now you could also do this integral by converting all of the cosines into sines. That would involve a term like 1 minus sine squared cubed, and that's going to involve a lot more work to expand that to make it happen. It's equivalent, but it'll work out the same way. Now for the second integral, we need to compute the integral of sine to the 4th of x. Now since we have an even power of sine here, we're going to need to use half angle formulas to reduce this. So the key formula we need here is the fact that sine squared of x is 1 minus cosine of 2x all over 2. And so if I plug that in, the integral then becomes integral of 1 minus cosine of 2x over 2 squared dx. And then I can expand out this expression here. If I expand that out, I will see a 1/4 out front from the 1/2 squared. I can pull it all the way to the front. 1 minus 2 cosine of 2x plus cosine squared of 2x. Now the first two of these terms I can integrate directly just as they are, right? 1 integrates to x, 2 cosine 2x integrates to a sine of 2x, differentiate sine 2x, I get 2 cosine 2x. But for this last part, I need to use another half angle formula. So cosine squared of 2x, I'll do separately here. I can rewrite as integral of 1 plus cosine of 4x over 2, because if I get rid of a squared, I double the input angle. And integrating this gives me a 1/2 x plus a sine of 4x over 8. Differentiate that will give me a cosine of 4x over 2 plus c. So I'm going to put that up in here. So then my final answer, combining all three of these terms, is a 1/4. I have an x. I have a sine of 2x. I have a 1/2 x, a sine of 4x over 8. So then a plus c. Or combine the two x terms, I will see that's a 3/2, so 3/8 x plus sine of 2x over 4 plus sine of 4x over 32 plus c. Let's go work about the second integral using half angle formulas and reduction to get to the antiderivative.